Thank you for this opportunity to tell about this particular work of ours. This is joint work with a PhD student, Nidhin Koshi Vaidyan. So I'm going to begin with a small experiment. So in the next slide, you're actually going to see 20 images, of which 19 of them are of one kind, and there is one oddball. And your goal is to essentially find out where the oddball is as quickly as possible, and you should do it without guessing. I'll need one volunteer to put up his or her hand as soon as he finishes identifying where the oddball is. And so I'll volunteer the chair of this session to put your hand up once you know where the oddball is. So are you ready?
So just to understand, so I put my hand up when I identify the oddball.
Yeah, where the oddball is, yes. The moment you know where the oddball is, put your hand up. Okay, so 1, 2, 3. Okay, so the oddball is in the second row on the fourth column, that's over here. And I'll use the mouse so that those who will watch it afterwards will be able to see what's happening here. So I'm sure all of you were essentially searching for where the oddball was. He was rather quick in identifying where it was, but oftentimes people take a little longer. And here are some features in the search that you would have executed. So for example, the goal was to find where the oddball is and in the shortest possible time. Okay? And so here the cost is essentially equal to the delay that you take to make a decision of where the oddball is. Your search was, so these are things I hope you would kind of agree with based on your own search. And if you disagree, do let me know, because these are interesting things to essentially take into account and update the model for this visual search. Your search was perhaps based on local focus. So these two images were rather close to each other, that you had to essentially look a little carefully in each of the images. And when you did that, your attention was focused on that image and not on the others. And when you do that, you actually get limited information per view. Okay? So that's a constraint. On the other hand, you could control where you wanted to focus next. So when you do the search, you go to the next position. And when you go to the next position, that next position is something that you can decide where. Okay, so that's another feature. A third feature is I actually didn't tell you what the two images were. So somehow you figured that there were many images of the same variety. Of course, I gave you that information, but you figured that these two are of a similar variety and it's different from this particular image. And that enabled you to distinguish the oddball image. In doing this, you perhaps didn't wait until you nailed the picture down. You didn't come to a description in your mind. You didn't articulate that it was the solid rectangle on top with the open rectangle or white rectangle on the bottom. You didn't wait until you were able to articulate this in your mind. You just waited until you knew that it was different. So that's another feature. You also waited until you were quite sure about where the oddball location is. The way to essentially, I said no guessing, so to that extent you were pretty sure. The way to model this would be, we have to take into account asymptotics of a certain probability of error. When you stop, you say that this is the place where the oddball is. We want to essentially make the probability of error go down to 0. So these are features that we must take into our modeling. There are many others. I'll just point out one which we haven't taken into account in this work. When you switch from one location to another, you actually lose some crucial milliseconds, which is between 10 and up to 200 milliseconds, depending on the length of the move. That's called a saccade. This move from one focus to another is called a saccade, and that costs you some amount of time. And we said that here the cost is essentially the delay to a decision. So when there is such a cost, you have to essentially take that also into account when you make the decisions. But for the purpose of today's talk, I'll not deal with that particular aspect. There are many other features. I'll be happy to hear your comments and maybe try to incorporate them in future works. So I would like to now take into account the features that I described in the previous slide and come up with a model for visual search. And this model is going to be one of control. So it's control with limited information that you can gather at each stage. So I realize that many of you may not have encountered such formulations before, so I'll try to spend a little bit of time explaining the formulation here. For simplicity, assume that we have only one sensory neuron. Okay, so the input to our brains is essentially through only one sensory neuron. And let's also, for simplicity, assume that time is slotted, and the unit of the slot is 1 second. You decide where to look at the beginning of slots, okay, and this is based on past observations. So that's the control that you have. You have a history of your past observations and actions, and you determine where to look next. Let's say that you decide to focus on location A subscript n in the nth time slot. This A subscript n is going to be one of the k locations here, and the k was 20 in the example that you looked at. Okay. And you do this at the beginning of slot n. Now, when you look at a particular location, the object there is either the oddball, which is the solid rectangle on top of the white rectangle, or it is the distractor. I call the other 19 objects, other k-1 objects, distractors. And these distractors are of a different variety. Now, when you look at the, what is the observation that you get? When you look at the oddball location, your sensory neuron now responds in a certain way. So this is a stimulus to the sensory neuron, and the neuron starts responding, which we model as a Poisson point process with firing, whose rate of firing is R1, okay, if the location where you're looking at contains the oddball target. So that's, if the location that you're looking at contains the oddball target, your observation is a Poisson point process. Of course, you're looking for only one time slot, and this one time slot is of duration 1 second. So the number, what you will observe is a certain number of points, and for those familiar with sufficient statistics, it's enough to keep just the number of points in this particular slot. And so the observation can be taken to be a Poisson random variable whose parameter is R1. Okay. Now, if you happen to look at a position where there is a distractor, your observation is a Poisson random variable with the parameter R2. Okay, the rate is R2, your time slot is 1 duration, so Poisson random variable with R2 times 1, and that's the parameter R2. Now, the point here is, of course, that we do not know what the rates R1 and R2 are. We don't know what, how the neuron responds to these two images, and that's where the learning aspect comes into the picture. And I call this the configuration. Configuration is a triplet. It contains the odd ball location. It also contains what's the rate of the firings when you look at the oddball target, and what's the rate of the response when you look at the distractor. So I, R1, and R2. So I stands for the oddball location, R1 for the response rate when you look at the oddball location, and R2 the response rate when you look at the distractor location. And all of these are only for one neuron. Of course, it's fairly straightforward to generalize this to under idealized assumptions to multiple neurons when they are independent, when they are firing independently and so on. Yes, please.
Just to understand the model a bit better. So we have only one oddball?
We have only one oddball. I tell you that up front, yes. So I think you're perhaps thinking of the locations of these images as being points of a Poisson point process. No, that's not the case here. So you're just given several locations. In each location, you have either an oddball or a distractor, and you can choose where you want to go. When you focus on a particular location, let's say that location contains the oddball, then you drink in the image that's there, and the response is essentially fed to a decision-making entity. That response is now firings, which is a response to this particular stimulus. If you look at a different location, which is not where the oddball is, the response is firings, spikes, and you count the number of spikes, and that's the signal that's sent to the further decision-making center. So that's the picture, whereas I think you're thinking of a geometric arrangement of the images on a line, so that's not the case. So the geometry of the arrangement is an important question in these modeling, but we don't, because that's something that I will speak about in the very last slide as an extension. This geometry does matter, but here we assume that it's inconsequential. Okay. Yes?
So it's incorrect to consider this as a change point detection problem?
It is not a change point detection problem because the state of nature or the ground truth is static. You're trying to figure out what the ground truth is. So maybe as I...
So it's a change point detection without knowing the prior and the posterior distribution?
There is no change. The state of nature does not change at all. The state of nature is the oddball. So if you go back to that first example that I gave you, the state of nature is the oddball is over there, and it doesn't change. You have to determine where the oddball is. Now, of course, you're controlling where you look and so on, what kind of data you get and so on. But that's entirely under your control. The true state of nature is static.
The ground state would be the distractor, and then the posterior would be the oddball.
No, you're trying to come up, maybe as I go through the model, let us see if my description answers your question. If not, I'll try to do it at the end, because I think it's an important question to address. So one could potentially think of modeling it the way you are doing, but I don't see a way immediately. But you will see that in my description, there is no change point. It's a hypothesis testing problem with control. Any other questions? Yes?
Memory you're assuming is
Infinite. You have unlimited memory. We will come to that in the end. Okay. I must describe what a policy is. When you do the search, you're actually executing a certain search policy. And the search policy is a sort of contingency plan that you come up with right at the beginning. And it's a rule book, and you just follow this rule book. At each instant, based on the entire history of what you have observed and all the actions that you have taken, you decide whether to stop or not to stop, whether to stop or to continue. And when you decide to stop, this rule book also tells, based on what you've observed, which is the oddball location. And when you decide not to stop, you're continuing to search. The rule book also tells you where to look next, or it gives a prescription on how to find out where to look next. Okay, so in a sense that where to look next could be a randomized strategy. And here is a piece of notation. The ground state or ground truth is psi, that's the configuration. And of course, you have a policy, and these two together will essentially determine the distribution of the observations and the actions that you have. And I denote that by this object here, which is p subscript psi superscript pi, just to indicate that these are involved in the description of the measure. And expectation with respect to this measure is going to be denoted as e psi pi. And this is all when the ground truth is, or the configuration is psi, and your policy is pi. Psi is unknown, yes. Yeah, you know that it's coming from I, R1, R2, but you don't know what it is, yes. Okay, our objective is essentially to minimize the time to a decision, and this will be modeled in terms of a stopping time, tau. This time, so this is the time at which you stop and you say, I'm done, I have a decision, when Aaron put up his hand. Its distribution, of course, is induced by the measure that we have, which depends on the ground state and the ground truth and the pi. And I'm going to essentially look at policies which are good policies. Okay, so what is a good policy? It's a policy that meets a certain epsilon probability of error criterion. When he put up his hand, he was he probably had in his mind a certain target probability of error, and only when it was below that did he put up his hand. And I don't know what his epsilon is here, but in any case, we'll look for policies of this variety. It's a set of policies that make an error with probability at most epsilon. And here by error, I mean your decision at the time of stoppage. If the decision is not the correct oddball location, we declare an error. Okay? So we want this particular error rate or the probability of an error here to be less than or equal to epsilon. And now this is actually something which is quite demanding because the probability of error should not exceed epsilon no matter what the underlying configuration is, no matter what the ground truth is. So this is actually we are demanding quite a bit from these policies. The expected time may of course depend on what the configuration is. So for example, if the two images elicit a response R1 and R2, where R1 is very close to R2, then chances are you have to wait for a very long time before you're certain. So the expected time can depend on R1 and R2. Wearing an analyst's hat for each psi, which is the ground truth or the underlying configuration, what I would like to find out is what is the minimum time for you to stop or for a good policy to stop amongst the class of policies which essentially work very well in the sense that the probability of error is less than or equal to epsilon on any configuration. Okay. So it is possible that you might take into account that the ground truth is psi here in coming up with this optimization, but I do demand that you do well, epsilon well, no matter on all the possible configurations. You could fine tune to this psi, but you must do well on all the configurations. So that's why this minimum is over all possible policies which attain a probability of error less than or equal to epsilon. You could fine tune it to psi, but then what we will see is we'll come up with a policy that doesn't depend on the psi, which is asymptotically optimal. But for the moment, we allow this particular fine tuning. But you better do well on all the other policies as well.
There's no bounds on the search space?
There is no bound. No, the search space is, I know that there are only k locations. Yeah. Now, otherwise, where the oddball is, things won't be tight here. So, okay. So the expect.
Sorry, and this is fixed.
K is fixed, and you know that up front. 20 images. Okay. We anticipate that as you drive the probability of error down to 0, you're going to take longer and longer because you have to do well no matter what the underlying configuration is. And if you study this a little, or if you're familiar with Wald's identities and Wald's initial classical results, you will recognize that the expected time is going to be of the order of log 1 over epsilon times a constant. And so the right normalization is you have to get rid of this log 1 over epsilon, and we drive the epsilon down to 0. And that essentially gives us some constant which I define, which could depend on the configuration. I define that as 1 over d xi star. Now, by symmetry, it perhaps is intuitive that where, the oddball location, this d xi star, should not depend on the oddball location I. That's because we have essentially thrown the geometry of the particular configuration out of the window, and we are focusing only on I, R1, and R2, and I could be any particular location, and there is symmetry here. Between I and J, there isn't any particular geometric relation that we are taking into account, so it must be symmetric to this particular, it must be independent of the I. So there is some invariance to the location, actual location I. And so this D star must be something that depends only on the two images, only on the response to the two images, which is R1 and R2. And we could take this as essentially a measure of how different the oddball is from the distractor. Okay? So this is the message that we will take forward. And our goal will also be to try to understand how to solve this particular problem here. Okay, after this introduction, I'll now come to the motivation, why I'm actually interested in studying this problem. Neuroscientists have been looking to quantify what are called perceptual distances between objects. And these are as opposed to pixel distances. So two images which are very far apart in pixel space are actually things that we are able to identify rather quickly. Two faces, two different faces, we know right away that this is this particular individual, this is some other individual. So we are able to distinguish faces very quickly, but machines which largely focus on pixels and extract features from them find it a little difficult to essentially do this as well as we do. On the other hand, there are two images which are essentially very far apart in pixel space. So for every pixel which takes value between 0 and 255, you essentially look at that number minus 255 minus that number modulo 255. And that gives you, or you just add 128 modulo 255. I think that's probably a better thing to do. Then this is, each pixel is 128 units away from the corresponding pixel in the other image. And of course, this will be very quickly detected, but we find it very difficult. A machine would detect it rather easily, but we find it very difficult to distinguish between these two images. So the way these things are stored in our brains, it essentially gives us a means to, these images are represented in our brains. We are able to identify certain images much better than machines, which possibly use pixel distances. And there are some others that we find very difficult. And so can we quantify these perceptual distances? And the way neuroscientists do this is via this ingenious method. They actually do experiments of the sort that I did at the beginning of this talk. They present oddball A among distractors B, and they find the average search time, and they just assign perceptual distance to be equal to the inverse of the average search time. When I got introduced to this problem, I got introduced to this problem in exactly this way, where someone presented that we want to look at perceptual distances, and then they, this particular researcher, neuroscientist, he essentially said perceptual distance is inverse of the search time. And it wasn't clear to me why it ought to be the inverse, and if the inverse, what function of search time should you look at, and if there is some other function of the underlying representations that we could take into account here. And so it was to address these questions that I looked into this with my PhD student. Okay, the inverse of the search time from our modeling is actually proportional to D star, and so D star ought to be one substitute for the perceptual distance between the two images. Now, just to repeat what I just said, such search time experiments and quantification of D star, they help understand how images are represented in the brain to some extent. And they also tell what features are important and how, in another interesting application of such things, how distances can add up in perceptual space. So you introduce two images A, and B is a slight variation of A. And then you introduce another C, which is another slight variation of B itself. And so you have added distance, you have added an extra feature. But then if you look at A and just the third, and the difference between B and C alone added to A, do you get the kind of additive distances, or are distances not additive? So these are interesting questions that neuroscientists are interested in. And so hopefully some of the things that we are looking at will help them at least model and get a better perspective of how the distances behave and so on. So if you're we have analyzed some actual experimental results. So if you're interested in these experimental results, there is a paper that you can get from arXiv. And here, the search time amongst human subjects to identify a certain oddball was found to correlate very well with the inverse of D star, which is the distance or some, d star is the quantity that I said, but that I had introduced in the previous slide. But this is something that depends on the responses. And so these responses were obtained by making measurements on macaque monkeys. And like, for example, you find out what the R1 is on this particular image, what the R2 is on the other image. And you look at d star, which I haven't told what it is yet, but you compute the d star, and you identify that, well, this correlates really well with the search times in human beings. Yes?
How do you choose K, or is the K for humans the same as for the monkeys?
So there are a lot of, one can raise a lot of questions here. For example, the K for monkeys was 1. So the monkeys were shown a particular image. Whereas for humans, the K was 6 and they were arranged in a hexagonal pattern. So you can say that in humans, the arrangement could have essentially affected the way they were reading these images. And that could be different from what response one sees in monkeys. That's a perfectly valid point. And also there are other things. This is making the assumption that the kind of processing that we do is similar to the kind of processing that happens in monkeys. But of course, we are very well trained to capture certain kinds of images. So letter, we can read and write, and that essentially says that we have some specialized neurons for recognizing letters, recognizing certain patterns that we have come across during our training, and that could influence the way we essentially respond to these images. And so these are questions that the neuroscientists have looked at. I am not qualified to answer them, though. There is a question there.
In the humans, you do the experiment only once, or do you repeat it?
Oh, it's repeated several times. Each subject is shown not just one image, they are shown several images, and they're all interleaved.
You know that it's always hexagonal, so for example.
I know that it's always hexagonal, but I don't know which of the 6 locations it's going to be in.
Because, for example, at least for me, there's some loss of time in just understanding how the things are.
Yeah, so yeah, we tell the subject that this is how it's going to be, and then there are some practice tests, and then comes the real test when we take the measurements. Yes?
Is this star just the divergence between the two?
Okay, yes, almost, except that there is control. So if you don't, I'll come to that. Yeah. The D star is related to the divergence. When there are just these 2 locations, and you want to, I'll come to that. Okay, so how many more minutes do I have, Aaron? 7 minutes, okay. So I might not be able to do justice to the analysis, but I'll just point out the key elements of the analysis. Okay, so this perhaps suggests if you're doing it, if this correlation is matching perfectly, maybe we are actually searching in an ideal fashion. Okay, but of course, more nuanced models are needed, and a variety of experiments are needed to confirm this particular hypothesis, and that's also something that our neuroscientists friends are looking at. Okay, the rest of the talk is going to be somewhat shortened now. Given a configuration, I would like to determine what the closest alternative is, and then discuss the converse. I may not have much time to go over this, because I would like to give some time for discussion, but I'll just tell what the key ideas are. And I'll also, here you will see whether relative entropy enters into the picture. So we'll get, and these 2 things I think I will not be able to speak about. Okay, so the converse is, as always, via this particular data processing inequality. And therefore, you will automatically recognize that somehow relative entropy is going to enter into the picture here. So suppose, and I'm sure most of the audience here will be familiar with it, except that perhaps this is an application of this particular inequality in a setting with stopping. And so that's what probably is marginally different from what you might be used to. So suppose we have a random variable x, and we are trying to distinguish between two possible distributions that this x can take. So the ground truth could be either 0 or 1, and when it is 0, x is distributed according to P0. When it's 1, x is distributed according to P1. And you do some processing, and out comes your y. You like to do this hypothesis testing. Now, your ability to distinguish between these two hypotheses is given by this relative entropy between P0 and P1 when you're operating on the input side. But if you do some processing, let's say you get a y, then there are these induced distributions for P0 and P1. Under hypothesis H0, y is now distributed according to Q0, and under hypothesis H1, y is distributed according to Q1. Then such processing can only decrease your ability to distinguish between the two hypotheses. And this is reflected in this inequality, that the relative entropy at the left side is greater than or equal to the relative entropy on the right side. Okay, so how do you apply this particular inequality? So this is going to be the central idea to get the lower bound. So let's say that we have two configurations, I, R1, R2. The oddball location is at I. The response rate on the oddball is R1, and the response rate on the distractor is R2. And let's say that there is another candidate configuration. Yes, there is another candidate configuration, J, R1 prime, and R2 prime, where J is not equal to I. These are two configurations that differ on the oddball location. Now, suppose you propose a policy, then what I will do is I will use this particular policy on the ground truth psi. Okay? And I'll also compare it against a psi prime which is of my choosing, and it will be chosen to baffle your policy. And so this is sort of the nearest stumbling block. How long you take to essentially distinguish between psi and psi prime is essentially what's going to determine the time that you take, and I'll choose the worst possible psi prime for your psi, and that will determine the expected time. So it's all data processing inequality to get the lower bound and nothing else. And I'll now quickly go to what the bound is. Let's see. I had quite a bit here, but I'll skip all of those things. So just focus on the last item here. One can show that the expected time is going to be greater than or equal to a log of 1 over epsilon divided by d star. And I'll tell you what d star is, and for this I'll have to go back a little bit. This d star, you have to focus on this particular section. The d star is essentially given by for a given policy that you might have to essentially identify where the odd target is, and this is a randomized policy for looking at a particular location. That randomized policy is given by lambda. What the nearest stumbling block is something that minimizes the average relative entropy, where the average is essentially based on this lambda A, which is here, lambda A, and this is the average relative entropy. And you try, for a particular lambda, you have this average relative entropy between the distributions for the observation when the ground truth is xi and your action is A, and the ground truth is xi prime and the action is once again A. And you try to find out what's the best or the toughest psi prime to essentially distinguish from this psi. And of course, your policy is guarding against this particular psi prime. And the resulting performance that you get, which is this average relative entropy, is this d star. And it's because of this control that enters into the picture that it's not just relative entropy, but this optimized relative entropy. So I think I'll now just jump to the final result. I'll just put that here. There is a policy that you can get to. So here's the final result, and then I'll stop with this. For learning to detect the oddball target with Poisson observations, the performance is essentially given by 1 over d star, where this d star is the average relative entropy, where you are trying to, the person who's doing the search is trying to guard against the worst possible alternative. And that is a policy that essentially gets us this particular performance. And one can actually come up with a means by which you don't have to maintain the entire history, but you can just maintain posteriors, and these posteriors, in the case of this Poisson observations, are rather simple to maintain. Okay, so I'll ask you to focus on the last bullet here. There are many open questions. What if there are 2 images instead of 2 oddballs? Okay, so I can't call it oddball anymore, 2 even balls instead of 1 oddball. There are also other such experiments. So neuroscientists cook up experiments to test several hypotheses, and each of them have to be modeled in a somewhat different way. Perhaps there is a paradigm that one can come up with in trying to handle a whole lot of these problems. How do you model similar other experiments? The cost of saccards have to be taken into account, and that's a finer detail that would be interesting to look at. When you search, you actually do a broad search first, which is rather shallow, followed by a narrow and deep search to essentially zoom in to a particular locality and then pinpoint where the odd one is. Can we do something of this sort? And also, what if your distributions are no longer Poisson random variables? Poisson random variables are still coming from a parametric family. What if these are general distributions? So with that, I'll stop. Thank you very much.